Much, Natasha, and really excited to be here with you all. This is one of my favorite topics, and I have a lot to share, so I'm going to do my best to keep it concise. I could probably give a 6-hour lecture on just this one slideshow tonight, and it's covering a lot of topics, and so I'm going to we're just going to be skimming the surface of a lot of different aspects of geology and the geohazards and the fracking operations here. So thank you. So just very briefly, who am I to be talking to you about geology? This has been my love language for a very long time. I started in 1998 in the geology program, so I'm dating myself here. And I have spent a total of 9 years in higher academia studying geology. I am not actually a practicing geologist, although it is my greatest love. I became an entrepreneur in 2019, actually, after leaving a PhD program in geophysics. And I'm really happy to be on the path that I'm on. And also, volcanoes have become the brand of my business. And so it is still very much part of what I do all the time. But really, everything that I have done in my life has been around learning the language of Earth. And that is what I want to bring to you tonight, and to share and to understand the stories, to be able to look around you and to see the history, to see the stories, to have a greater appreciation for this incredible place where we live. It's actually geologically very unique. So that's me. Okay. So briefly, what is geology? Obviously, it's the study of rocks, but really rocks are the vehicle for us to learn those stories of the landscape. So it is a very dynamic process. It's a dynamic science. The Earth is actually, although we see it as static, it's constantly changing. It's just changing on a very large time scale, and sometimes on a short time scale. So it is a constantly evolving language of the Earth. And I want to give you an anchor of place, like to really orient you here tonight to our place and to the way that we can engage and advocate for our landscape and for especially the public lands that are just on the periphery of town. Geology is a lot of arm waving, and true geologists are out in the field, like not true geologists, but you will often see geologists out in the field with their beers and waving their arms around and having great debates. And that's one of the fun things about geology, because we are looking at the evidence of the Earth that is around us, and we don't have definitive answers. So we have best guesses, we have theories, we have hypotheses. So I can promise you some arm waving tonight and a lot of maps, which is also what you will typically see geologists doing. And that is what tells us about the landscape here. So my intentions, again, are just to inspire you to feel more connected, to feel more appreciation for the land, and to orient you, and then ultimately to give a call to action, because with the new changes and regulations, with the current administration, we need to be more aware. This is about education and knowledge as power and as advocacy. It's not about demonizing any of the operations that are happening, but just about understanding them so that we can really come together as a community and defend the resources that we have here in our very special area. Okay, so I would like to start with a map. This is the geologic map of Colorado. I would like to acknowledge the many geologists that have done many years of work to create this map, and we have some in our valley, David No being one that maybe some of you know. And thank you to him for doing so much incredible groundwork so that now someone like me can come along. I've been here for 4 years and can read and understand without actually having to go and look at all of those rocks like by myself, which is a long process. So thank you to these geologists. I know there's just a lot going on here, and I just want to without going into a lot of detail about what we're actually looking at, this is the plains, and then we can see the line of the Rockies here. And then we see a lot of these red areas and pink areas over here, and these are volcanics. And we are actually in such a unique area. I'm going to show you on the map where we are and orient you to where we are. But basically, we are where there's a feature called the Colorado Plateau, which I'm going to share a lot about. And it is meeting the Rocky Mountains. So these are the Rocky Mountains. This is the Colorado Plateau. And so where we are here in this North Fork and Roaring Fork Valley area is the meeting place of those two, which is really unique. So we are actually standing on the Colorado Plateau, not technically in the Rockies right here. And when we look at our mountains, so Mount Lamborn and Land's End they are like defining where that boundary zone is. So we are actually inhabiting that boundary zone. And I'll explain more about what that means. Okay. One thing I want to say as we get started is I just want to share a short story about, as a volcanologist, something that really came home to me about what happens in the landscape and how it can affect us, and like what we don't know can hurt us. And so that was also part of my inspiration in this talk tonight, is to share what it is that maybe we don't know because we're not looking at all the time, but it is right here. It's in our watershed. It's in our backyard. And the story I want to share is a volcano that erupted in 1985 called Nevado del Ruiz in Colombia. And it had been dormant. And so a lot of the local populations had no active stories in their mythologies of the volcano erupting. So when the scientists came and said, there's this activity, we want you to evacuate, they said, we don't believe you. We're not going anywhere. And so they didn't, and 23,000 people ended up dying because of the mud flows that happened with that eruption. So that's a really extreme example. And of course, we don't live in a volcanically active area like that. But we are receiving consequences from the things that are happening outside of our immediate area. And so that's what I want to orient us into. And this is the Colorado Plateau. So you can see this outline, kind of this perfect little heart, right? Isn't that fun? So we are here in the very center of the continent. This is the Four Corners right here. So this is actually extending over 4 different states. We've got Colorado and Utah and Arizona and New Mexico. And it is about 140,000 square miles. What's unique about this is it is a total geologic anomaly and mystery. And it's the only place like it in the whole world where there has been, in the very center of the continent, a piece of crust that has stayed together undeformed despite mountain building activities, and has actually never been deformed. So we are living on like original crust right here. And it became a pressure valve. So I'm going to share a timeline of the geologic history of our area. But basically, the Rocky Mountains were created by what was called the Laramide orogeny. And that was a plate crashing into the west coast way over here. And all of that pressure got translated and ended up popping the Rockies up, right? Well, it bypassed the Colorado Plateau. So all of that pressure, instead of deforming it, it twisted it and it lifted up and it turned. So it's like this, literally like a pressure valve that happened. And all along the edges and in the interior, too, is really unique volcanics that we don't see anywhere else in the world. So in the very center of the Colorado Plateau, we have volcanics that have a chemical signature of literally having come straight from the core mantle boundary, like deep, deep, deep earth, right? Which this is very unusual, that they came and they basically came all the way up and they punched through this Colorado Plateau, which is thick continental crust, without stopping. And the reason this is unusual is because normally what happens is the volcanics come up, they kind of melt the surrounding rock, the composition changes, they become more silica enriched, and then they come up a little more, and they basically melt their way up. And by the time they erupt at the surface, they have a chemical composition that has a lot of that signature of the continental crust that they've moved through. In the case of the Colorado Plateau, we don't see a single signature of our continental crust. So that indicates these volcanics were fast. They were very fluidal, non-viscous, and they just punched right through. And all along the edges are additional volcanics that have a little bit different signatures. And so that's actually where we are. We are in a volcanic area that is because of the plateau. So along the edges, this is all weakened area all around the edges. And so it becomes an easy place for those volcanics to make their way up. Okay, May. So this is our general area, and this yellow circle we're going to look at from a lot of different angles on a lot of different maps. This is the Grand Mesa right here. So you can see this is basically like Hotchkiss is right there, like Paonia is like right here. This is Lambourne and Land's End. So you can see we're right in that transitional zone. This red circle is where we're going to be zooming in on the oil and gas, just the gas operations. And one more, May, and then that's where we are right here. Just to orient us here to the bigger picture. So this is that big yellow circle, and I just want to orient you where that is. So basically, we're starting down here at the Black Canyon, and then this is just our circle for our circle. It's not like, this is just where we're orienting. But this line is the Colorado Plateau, the edge. And so we're looking at this bigger area going all the way from Palisade to Rifle, and this is kind of our bigger geologic neighborhood. This is, like I said, that edge, and so it comes basically, it crosses the 70, and then it basically follows the 82 all the way down to Carbondale, and then it picks up the 133, or we should say the 133 and the 82 pick up this zone of weakness as a natural corridor, and it follows the 133 basically from Marble all the way to Kepler's Corner right here. And then instead of following the 133 around, it kind of just skirts the edges of the mountains like that. And then it goes all the way skirting the edges of the mountain down to Ridgeway, and then down to Durango, and goes on from there. So geologically, that is unfortunately kind of blended in with this projector, but this is that same circle, just to give you an idea of what this looks like. And so again, we see these are the volcanics. Well, these are laccoliths. They're actually not volcanics. The red is volcanics that have actually erupted onto the surface, like Grand Mesa. What we call laccoliths would have fed volcanoes, but they're actually called intrusive rocks, so they cooled underground rather than getting erupted out to the surface and cooling above ground. But these are a lot of our, goes into the mountains that we see around Marble and the Maroon Bells and Mount Sopris, and then of course ours down here with the Elks are all part of that same complex. So these would have come up along that edge of weakness and fed volcanic complexes that we don't see anymore. So we'll talk a little bit about needle rock, but that's exactly what needle rock is. So needle rock would have been fed by the magma chambers of Land's End and of the mountains that we see around Crawford. That's our best guess. Like they would have been channeling into this conduit that if we dug into a volcano about a mile deep, we would find something about like needle rock. And so that's the actual conduit where the magma was coming up. Okay, so I just want to show you these side by side so you can kind of orient yourself with, this is just our Google map. This is Paonia hiding underneath all of these. This is just my Google map, so I've got a lot of things marked on here. But yeah, so just so you can see, this is of course the Black Canyon down here, and again, these volcanics. And so you can really see the difference in geology on one side of that line and the other. Again, this is the Grand Mesa. And I'll share a little more about all of these features as we move on. Yeah.
I have a question. Are the laccoliths the ones that hold the mineral signature of the deep rock?
No, that's a good question. So those that I talked about that have the really deep, those are in the interior of the Colorado Plateau. So for like part of my master's work, I worked on the Hopi Buttes, which are in the Navajo Reservation, and they have that signature. So they are buttes similar to Grand Mesa, but smaller. While we're talking about buttes, I can just explain what they are and why they're unique. They basically are a series of eruptions that happens where the magma will come up, and instead of building a volcano up, it encounters groundwater. They're very, very explosive. So you actually get reverse volcanoes. They're called Mars, M-A-A-R. And eventually the water gets used up, and then the magma the lava fills. It's magma when it's underground. As soon as it sees the air, it becomes lava. It's the same thing. So the lava then fills that depression. And so that's like what we see on the top of Grand Mesa was actually 27 of those. And then the lava fills the ground surface. So like it would just fill exactly what the ground surface looks like right now. It's not building up, up, up. But then what happens with time is that becomes like a hard erosion resistant cap. And so then it stays. And in the case of the Colorado Plateau, which uplifted almost a mile, and we'll talk about that a little bit more too, but because of that massive uplift, the erosion rate increased. So everything erodes away from that cap. And so then you get this mesa that's preserved. So that's how they're formed.
I remember David Noe talking about the laccoliths being those kind of pointy pyramidal things.
Right.
So if laccoliths are underground.
Well, then everything got lifted up. So our mountains were formed underground, a mile underground.
Okay, and so all of the West rocks that we see are laccoliths, not just these pointy things?
They are laccoliths, and they have been eroded by glaciers and other things. Yeah. But I did hear that on his interview just today as I was listening to that this morning, that he talks about how they more or less have the same shape now that they did underground, although the glaciations can really be intense on a rock. So, and we're going to look at that too, how we can really see those features in our landscape. And that's actually what our cities, Paonia, I call it the Tri-Cities, Paonia, Hotchkiss, and Crawford, we are built on a lot of glacial sediment and a lot of wind-blown sediment, and that is part of what makes this area hazardous. And so we'll actually go into that at length. Okay, so just to reorient us again, that's where we've just looked. And so now we're going to zoom in here to this red circle. So, okay, so this is what we call the Southeast Piceance Basin. That's what I'm going to refer to it as. That's what oil and gas refers to it as. The Piceance Basin extends all the way up to Grand Junction. And we are at the very tail end here. That's exactly what this is. This is the tail end, the southeast end of that basin. I'll explain more about what that basin is too. But just to see where this is, so Paonia is just off the map here. This is Bowie and Somerset. This is the Hubbard Creek watershed. This is the reservoir right here. And of course, the 133 skirts along. And then this is the west and the east Muddy Creek. And so these are those watersheds. This is the East Muddy Creek watershed, West Muddy Creek watershed, and the Hubbard Creek watershed. All of those funnel into the North Fork of the Gunnison and come down to Paonia. Okay, so we receive directly everything that happens in this red circle. And this is the geology, just so you can kind of see what that looks like. You'll see a lot of cues, and these cues are basically quaternary reworked material is what we call it. And what that means is that it's already loose, it's glacial, it's fluvial. Fluvial is coming from rivers. Aeolian is coming from wind. It's a lot of just loosely deposited sediments that slump and have landslides and reslump. And so that's what we're built on. Like, we're not really built on solid foundational rock here. We're built on reworked sediment. So it was already loosely consolidated. It gets reworked. It just continues to be like poorly settled, you know. So there's subsidence that can happen. There's a lot of clays. This is all sediment. Clays can be expansive and then they contract, so that can cause problems with construction. A lot of compaction will happen where suddenly the grains will come into greater sorting and everything on top of it comes down with it, if that makes sense. So it's like it fills the spaces up. So we're in a dynamic area, basically. And this area is especially dynamic, and this is actually where most of the landslides that have been recorded in our area have been recorded. So this is where the fracking operations and the landslides are. Geologically, that's an interesting combination. Okay, next. This is what that looks like. So this is our same red circle. So everything that you see here is public lands that have been divided into leases. So that's what all of these boxes are. The blue circles are active wells. These are actively producing. The yellow circles are shut in, or they've been capped, but that doesn't mean they're actually not producing. It just means that they're not being monitored. But a lot of those productions, the gas can escape through the well and through the fracking, the well casings itself too. So just because they're shut in doesn't mean we get to pretend like they don't exist. They are still a fracked well. So anyway, this is huge, a huge area. And it's literally our backyard, but we don't always see it. I want to just again emphasize, these are our resources. So I'm not here to demonize the extraction of natural gas. We have an abundance of it. We need to have a say as the residents who live here and who are impacted by especially the pollution in the air and the groundwater. We need to be educated, and we need to be advocating for a sustainable and strategic long-term plan that puts the health of the citizens of this area first. So, okay. This is the bigger picture. So now we're zooming out to our big yellow circle. So we're looking back up to Palisade and Grand Junction out here. So this is the Piance Basin. You can see there's a lot of leases. Most of these are on public lands. Huge operations happening here. This is on the other side of our watershed. You know, huge operations happening. So we have relatively fewer wells, and Gunnison County has a lot more wells than Delta County. But you can still see where, you know, this is a desirable area. I have to just look at my notes here. Okay. All right, wait, May, thank you. So to very briefly orient us with the watersheds, I kind of touched on that, but I know there's a lot going on this map, but I just want to point out these blue. This is basically 3 watersheds kind of combined, the Hubbard Creek and North Fork of the Gunnison watersheds. This is Paonia. And these are fed by the West Muddy Creek and the East Muddy Creek. So that's what these watersheds look like. And then, yeah, Paonia here. So, and then going down to Hotchkiss. And then this is just, we have so much water. I mean, this is agricultural land, right? So we've got ditches, we've got all kinds of things going on. So these are all of the waterways that are, again, being, you know, fed into and affected by what's happening within this bigger watershed. Okay. This is a different red circle, but I wanted to include this map. This is obviously an illustration, but it's a beautifully done one, and I think it gives a great perspective of where we actually are and what we're looking at. So thank you, James, for putting this online. And this is our Tri-Cities here. And then here is this area that we're talking about. So this is our red circle is up here. And you can really see the change in elevation. That's what I like about this map. And we're going to look at this map again for when we talk about glaciers. But for now, we're just notice how much elevation there is, and we don't really notice it. It's not as in our face as the mountains are. But all of that, of course, is feeding these watersheds. So just to, again, emphasize that what we don't know can hurt us. Yeah, okay, next, please. Okay, I could probably spend a full 2 hours just on this slide. This is kind of the meat and potatoes of the geologic history. I could do a whole slideshow just on this slide, but I would like to just go through this as quickly as I can because there is a lot to cover. But I want to tell the story of our land. And this is a geologic time scale. And so we start always at the oldest on the bottom, and then it gets younger at the top. So this is here. And we're going to start on the bottom, which is that we see the oldest rocks all the way down here, Precambrian basement. This is like somewhere in here. That's what we go and look at in the Black Canyon. So there's some of the oldest rocks that we know of, like ever. So we're really, really lucky here. We get to go, and Black Canyon is a marvel of a place, I'm sure, as you all appreciate too. And then we have all of these Paleozoic and Mesozoic shales. I'm just very broadly lumping all of those together because you can see this is a huge amount of time. But this is the deposits that are causing, or that have created the coal and the natural gas. They are in this level of sediment. Okay, and so then starting here, 80 to 35, so we go from here to here. I should add before I do that, we have a lot of activity in the Cretaceous area, and you may hear these are when a lot of seas came, shallow seas, and a lot of, we basically were kind of the mid-continental ocean at that time, and kind of came and went, and so we have a lot of different size sediments. Some of them are shales, some of them are sandstones, some of them are limestones, like marble is metamorphosed limestone. But all of them are from from this time period where, especially in the Cretaceous, we have the seas coming and going. Okay, and so then as that is happening, the Laramide orogeny starts, and that is this plate way over there on the west coast, the Farallon plate, which is subducting underneath the western edge of the United States, or the North America, I should say, what is now North America. And the pressure from that pushed, and it didn't actually pop the mountains up until Colorado, the Rockies. So there's this massive swath from California to Colorado that translated all of that pressure. And so we are here where the rocks started lifting up, made the mountains. It took a long time, several million years. During that whole time, again, the Colorado Plateau was unaffected. Everything just bypassed it like an island. And during that time, the volcanics started, and we are considered to be, I wouldn't call it an active volcanic area, but we are in the realm of a potentially, technically we are in an active area. I'll just say that. But it's very small potentiality. But the youngest volcano in Colorado is Dot Cerro. You can actually see it on the 70. So if you pass Dot Cerro and you look up, if you're driving to Denver, you look up to your left, you can actually see the center and the crater of the volcano. And the lava flows cross the highway. The highway is built on top of them. And you can see them going all the way down to the river. So that is only 5,000 years old in geologic terms. That's like yesterday. And we have all these hot springs, so that's where they come from. So the mantle is what pushed the Colorado Plateau up. So even though we're here high, we're at like 7,000 feet, the mantle is much closer to us than it is in Denver by a lot. Like Denver is, full continental crust, all of that. We have like the mantle's right here. So it really is a unique place. So Needle Rock is about 28 million years ago, and that's the same time that's about the same age as our mountains here, Land's End and Lambourne. And so then, so just very briefly, the continental plate has crashed in, the Rockies have built. Now that plate has completely disappeared. It's completely subducted. There's no pressure anymore. And it's just like us, like if you're under a lot of stress and pressure, let's like bring yourself back to like finals time and maybe you're in school and you're pushing, and then everything's over and you have this massive decompression and your body wants to sleep and you need to stretch. So it's the same thing that happens with the land. Once that stress and that pressure is gone, everything starts to expand. So that expansion caused a lot of what we call the basin and range to the west of us. And it's also what the end of that expansion, it's like all that pressure got released and now the Colorado Plateau has nothing holding it, so it can pop up. So it started being formed 30 million years ago. It didn't pop up until 5 million years ago. Here. Really recent, relatively speaking. Yeah? So, and it popped up a whole mile plus, if you can imagine, in a really short amount of time. So the whole thing pops up, and now you have all these rivers, Colorado River, the Gunnison River, and they are now a mile higher than their output. So suddenly the rate of erosion is massive. So suddenly the canyons that we see on the Colorado Plateau make more sense. The Grand Canyon, the Black Canyon, right? So Grand Mesa is actually older than the Colorado Plateau, which is surprising. But again, it's all, this is all the same chapter, we'll call it. And then the last thing, there's other glaciations I didn't mention here. Of course, there's plenty of things I didn't mention here. But the ones that affect the landscape that we see are very young, so only 3 million years to 130,000 years. So they have really contributed to, again, the soils that we have and the landscape that we have. Okay, so kept it less than 2 hours. Okay, so this is a very technical map, and I don't want to go in too much detail, but I want to point out something really interesting. And this is the Piceance Basin, so this is actually a really nice visual. So if you can see this, the green here, and then the orange down here is the San Juan Volcanic. So we're kind of like right here. Okay. So these are cross sections broadly, where if you dig down and you start to look at the rocks that are below us, roughly this is what they look like. And so this is the Piceance Basin. This is that cross section. And I know that you can't read this, but the units that we're interested in are these. This is where all of the natural gas is trapped. So these units are the Unita Formation, the Green River Formation, the Wasatch Formation, Mesa Verde Group, and Williams Fork Formation. So these are called, we're going to go a little more into detail about fracking, but I do want to just introduce why this is unique here. So these are what are called unconventional deposits. In other words, you can't access them by conventional methods. So conventional methods are vertical drilling. Fracking came about because that didn't work for deposits like this, because basically what happened is those ecosystems got buried, like actual ecosystems, so these are natural, organic materials, got buried by sediments. Those sediments are very fine-grained, so shale is exceptionally fine-grained, and a lot of our sandstones are too, and so that means they're very tight, and there's no permeability. So the gases don't have anywhere to escape. They're stuck down there. But they're stuck in pockets. We can't really map where those pockets are. And there's no way to actually show where the edges of these formations are, right? You'll notice in this cross-section here, we don't see this blue unit, although we do talk about it around here. This is called the Manco Shale. You may have heard that. So we do have lenses of Manco Shale, but that is not a predominant unit that they're targeting in their fracking operations in the Southeast Piceance Basin. So we have what these are called tight gas deposits, and we do also have the coal bed methane, which is the methane that comes from the coal seams themselves. But those are two different techniques to retrieve that resource. And let's see. So these specifically the Mesa Verde and the Wasatch Group. Okay, the USGS put a report out in 2018, and this is partly why the Piceance Basin is so popular, that says they estimate there are 24 trillion cubic feet of gas just in those two formations. And that all of those 24 trillion cubic feet of gas are technically recoverable. So in other words, we frack until it's gone, and we'll get 24 trillion cubic feet of gas. That's the level of resource that we have. It's a lot. But technically recoverable means there needs to be a lot of operations, right? So fracking is horizontal, so when we drill, the conventional drilling is vertical. I might have just said that, but fracking goes it goes like a mile deep, and then it goes up to 3 miles horizontally. They have no idea what they're drilling into at 3 miles. You have absolutely no idea what the subsurface geology is like. You have no idea where the aquifers are. None of that has been mapped here. It's very hard to map. It's hard to map anywhere, right? So, okay. Actually, if we could go back a slide, May, I want to point out one more. One more. Sorry, one more. and one more. And one more. Okay, so this is just an example of how we really don't know. So this is this tiny little red dot. Okay? Here's where this tiny little red dot is. Somewhere above Bowie. This is a volcano, a volcanic deposit. Like, it's not even a deposit, it's like a volcano that nobody's talking about. Nobody's talking about it. I can't find a single published anything on it. I don't even know how to get to it. I haven't even seen it up close and personal, but I have seen it from the airplane. I've seen it from the eco flights that we've done with CHC. But just to show that as an example of that we really don't know. I mean, there is so much that has not been fully delineated in this area. Okay, thank you, May. Okay, how's everyone doing? Okay, so we have kind of 2 more sections of the talk. So this next section is geohazards. And then we're gonna close with a very short overview of how fracking actually works. Okay, so let's talk about geohazards, because we pretty much don't have a single square inch of this valley, of the North Fork Valley, that is not mapped as a geohazard. So I just want to let that sink in. I didn't know that until I was putting this talk together. So we don't really, by and large, have a public understanding of just how unstable the ground is here. Again, I want to show this map because this shows the results of the glaciers. So you can imagine that glaciers filled all of this, and that only these little white parts were sticking up, like little tiny. You can just imagine this a whole sheet of glacier. So that glacier is constantly pulverizing the rock underneath it, turns it into the finest, finest sediment. And so that's what all of these valleys are. You know, we have lots of different words for those, like cirques and arêtes and all of these things. But like you can see, where was it? One that's really nice. Anyway, you can see, like at the one, like Chair Mountain and Marble, you can see that really nice, clean edge. So that's very obvious glacial evidence. And so because all of this area is fed, and as those glaciers melt, it's all flooded. So all of this is just fully, like all of the erosion, all of the sediment that fills everything that we see here is all just this pulverized rock material that came from the glaciers, right? And has just been moved around by water and sand and wind, and then we build on it and we're surprised when our shed sinks, right? So this is the geologic map made by David No, part of the quadrangle of Paonia. And again, I just want to point out all of these cues. Everything you see pretty much is a cue. There's these tiny little islands of sandstone. Okay, those are solid ground. Everything else is reworked, poorly consolidated sediment. Okay. P?
What does Q stand?
Q is quaternary, so this is our recent past. Quaternary is the last, I'd have to look at the timeline again, but I want to say 20,000 years.
Unstable also?
Q is just a timeline marker, but because it's, Q is recent, so in other words, it's all that reworked stuff. Like we don't have any solid rock that comes with a Q. It's all just sediment. This is the very, very first geohazards map that I could find that was made of this valley in 1978. Actually, could you back up, May? I want to, before we move on, I want to actually, this is the only slide I'm going to talk about some of these things. Okay, so we've talked about the unstable slopes. The expansive soils are those clay deposits. Subsidence and collapse, same thing. This is because this is all the glacial reworked material. Rock falls, like when you're going up to past the reservoir, so those are not reworked materials. Those are what we would call primary deposits, but they're very crumbly. And even in the reworked, you know, these tongues that kind of come down off of Grand Mesa, you can see these tongues of material. We get rock falls. That particular unit going up past the Paonia Reservoir, I believe, is called the Green River Formation. That's what that one is. And we see tons of rocks on the highway because of that formation just constantly crumbling. So landslides are just a really natural event when you have very poorly consolidated material, and sometimes there's water and sometimes there's fire. When the fire leaves, there's nothing holding the rocks together, or like when the fire goes through and burns all the vegetation off. And so we will be focusing on landslides as far as the rest of the geohazards. I want to show you some pictures and talk about some of the more recent landslides. But I do want to address these, but we don't see these as much, but we can. So mud flows are basically a landslide that just gets more water when the water is bigger than the amount of earth, but then it becomes like liquefied, so it becomes a coherent. That's what makes them really damaging. It's not like water just, you know, it's like an emulsion, right? And then debris flows are not quite as much water as mud flows, but they still have quite a lot of water in them. Water can also trigger landslides without turning into a debris flow. So I just want to say all of that this is a continuum. It's not a definitive, and we absolutely are at risk here for all of these, given the right conditions, and especially given the warming of the climate and having changes in our in rainfall and all of these things. So you know, flooding is a big one too, especially when you think about burned areas. And one of the things that in these early reports I read about was sheet flooding, which is where it's not flooding like we see where the river overflows the bank, but it's we have a lot of really steep slopes here. And so you'll get these sheets of water that will come down these steep slopes and just take everything with it. So that's a hazard, and especially more locally, you know, you can think about a lot of these more, they're not on such a big scale of like, we all need to evacuate Paonia, but it's like, be aware about them, especially when it comes to construction and whatnot. And earthquakes, we don't have a lot. There have been a couple recorded earthquakes, but they're pretty few and far between. Mostly the hazard of earthquakes actually comes from the fracking operations because those have been shown to produce seismicity. And the seismicity is one of the biggest triggers of landslides. So the triggers of landslides are heavy rainfall, human activities, construction, or fracking, and the seismic, any seismic activity can cause a landslide. Volcanoes we talked about, that's obviously my great love, but we don't really have a lot of big geohazards here in the volcanic realm. Again, it's not out of the realm of possibility, but very, very improbable. Okay, so this was this first map. I believe this was made in 1978. And I know that you can't see these, but again, I just want to point out that this is Paonia over here. And every single square inch is mapped as a geohazard. And the entire valley up to up to Hotchkiss. So the North Fork area from Hotchkiss to the Paonia Reservoir, I didn't know this until I put this talk together, is listed as a Tier 1 ecosystem for for landslides. Tier 1. So it's been mapped and rated as highest hazard. So we're in the highest hazard statewide for landslides. And there have been a lot, and I just want to read a quote to you all to really bring this home. This is from a report in 2005, and this is from the USGS. And so they say this corridor from Paonia, from Hotchkiss to the reservoir, has a history of serious and frequent landslides. Irrigation ditches are both a victim and a contributor to instability of slopes. The most common factor in landslides is very steep foot slopes. So in other words, where those sediment toes are, which are our old landslide deposits themselves. Okay, and so they form these wedges that we see on the sides of the road. And that the instability is triggered by changes in soil moisture and disturbance such as construction. In 2002, this report was put together. In 2002, $1 million annually just in our valley is the cost of landslide maintenance. Did anyone know that? That was 23 years ago. What do you think it is today? And why we don't know about this? Like, I had no idea. So I was shocked to read that. Okay. Yeah.
So can you sort of paint a clear picture for me, maybe you're about to, of what the landslide threat is? Are you talking about like all the rocks you see on the road around the tour?
No, I'll show you some photos. This is just a decorative slide, but it's actually a decorative slide of data. So this is an actual landslide. I know you can't really see it, but this is our area. This is a photo from CHC. This is the map of all landslide deposits in the North Fork Valley. Here is Hotchkiss. Here is Paonia. The red and the yellow are exactly the same thing. The yellow just has more detail. So you can see a lot of yellow, like very finely detailed. They've mapped this with a lot more precision, but pretty much our whole valley. is mapped landslides. Okay. So it's, again, just bringing us back to this is geology, is understanding the subsurface by what we can see at the surface. And sometimes you do drill wells or drill holes to see what the characteristics of these different rocks are. And so subsurface geology is so important because, for instance, if there's a shale layer, a shale has what they call a very strong cleavage, which is that it has a clear, anyone who's looked at a shale, you know, you can see that obviously. There's one direction that it's flat, and then one direction you have to like break it and it's like a book, right? So if you have, like, let's say under the subsurface, you've got a shale layer at an angle. So you've got this impermeable layer of consolidated sediment, you know, mud that nothing can get through. And you have a really heavy rainfall and something triggers that. Everything on top of that shale layer can just, it's like a slide, you know? So that's the kind of condition that we need to be aware of. And again, because we don't really know what the subsurface geology is, we just don't know. We don't know when and why, and, you know, so that's why it's such a hazard. And it can cause a lot of damage. The fortunate thing about the landslides that we have locally is that they are what's called low runout. In other words, they don't become like 6-mile long things that, you know, go into the river channel and then take everything out. So we're not at that level of hazard, right? But the hazard is that, especially when you're looking in an area where they're fracking, you know, if all of that, if the landslide happened on active wells and everything gets ripped open, you know, that's just, nothing's contained anymore. So then we really have to worry about our water. This landslide was 2023, so probably a lot of you remember this, or were here for it. This is it's called Bear Creek. This is where that happened, and the highway, basically here is the river. So the highway was built over that channel, which was very poor planning, because these are very steep channels, and it would be a consideration that there could be a flood and something like this could happen. I mean, that's just engineering. So places where the highway is on the other side of, you know, like right here, you wouldn't have that kind of hazard right there. Because here's the drainage ditch, it goes into the river, and the highway's on the other side. Okay. So this one is East Muddy Creek. That's in our red circle. So this is in that, this is actually the reservoirs right here. So we've been looking at this area. This is actually on the like north side of the river. But these are some of the oldest mapped landslide. This is a landslide complex that's been mapped and monitored in our area since the 80s. And in 86, I believe it was 86, yeah, there was a whole emergency. It obliterated the highway. They couldn't even repair it. They had to move the whole highway. So this is how they're mapping them. And so they're moving slowly. It's a whole, you know, they're just, but the threat is that they get into the river above the dam, and that they can cause a lot of damage to the dam and then potentially downstream. So in 1986, they deposited 132,000 tons of sediment into the reservoir. So that is actually a lot of what we see when the water is low and you see those lines of sediment. That's what that's from, to the best of my understanding. Okay, and then one more we're going to look at. This is what a landslide can do, and this is in our area. This is Colbrand, which is just north of Electric Mountain, so it is on the other side of our watershed, but it is in that same area that we're looking at. This happened in 2014, and it's the longest landslide in recorded history in Colorado. It was unseasonably heavy rains that triggered it, and it became very coherent, you can see. It killed 3 people. It generated a 2.8 magnitude earthquake. And like I said, it was 3 miles, and it was 50 million meters squared of material, which is kind of hard to fathom. And at places, I don't think I wrote this down, but I think at places they were saying it was over 100 feet deep. So, I mean, if you had a landslide like that in our area, I mean, it would be absolutely devastating. And this is literally just right there. I mean, it's right there. So this is the same Piceance Basin material that we're talking about with the fracking operations. So this is the potential of what can happen. And we could have this happen on our side of the watershed. It's not inconceivable. Okay. Okay. So take a little pause. I know my little image didn't really show up very well. So I just want to end with an orientation around fracking itself, and just very basic. I want to share a disclaimer that I'm not a petroleum geologist. So if you have questions after what I've shared, I probably can't answer that specifically about the fracking. There's a lot to it. It's very complex. And yeah, so I just want to give a little overview. But basically, the reason natural gas is attractive is because it's quote unquote the cleanest of the hydrocarbons. So that's what this map is showing. This is coal. This is CO2 emissions by fuel type. So coal is at the top. This is oil, and this is gas. So you can see it's significantly lower, right? So it's like cleaner. So what is it used for? Heating, production, fertilizer, chemicals. Propane, it depends if gas is wet or dry. So when it comes through the fracking operation, can either, if it's wet, it has other liquids, hydrocarbon liquids like propane that can be additionally harvested. What we have here is typically dry gas, which means that it's much more straightforward and it's mostly methane. So, okay, you can go ahead. Thanks, May. So this is how it works. So this says shale fracking, but it's really any fracking. So in our case, we're not necessarily going through shale. But this is your, where the well gets installed, and they install this well casing. So that's a whole process in itself, is to just install the well itself. And that process, this is, okay, so before I move on to the water piece. So what happens is they install a well casing and they put cement around it to contain it. And then they inject at very high pressures a lot of water that are mixed with sand and a lot of chemicals. The reason for the mixture is that they need a certain viscosity, and that water gets forced down here and causes these cracks. So it's called fracturing because you are literally, it's fracking. It's because you're fracturing. You're fracturing open the rock. This is that tightly, the sandstone and whatnot that's not very permeable. So if you crack it open, and then because the pressure is so great, you have this mixture of sand and chemicals, the sand gets pushed into these cracks. So the sand fills these cracks and keeps them open. So they're basically, it's an installation. Once it's installed, it's installed. Like you don't have to keep installing it, okay? You just install it. But to install one well requires about, in our area, it requires about 6 million gallons of water for one well, for one fracking operation. That is about 1,500 water truck trips. So that is what is required, and what happens once a well is open is that all of that gross water, the reason for all the chemicals is because that's what gives it that particular viscosity. So for one well, you need about 100,000 gallons of chemicals, and they're gnarly. But it gives it that viscosity, and it also helps. They use for all kinds of different things. They just like keep the scale from building up inside, and to keep everything open, and all of that. So then what happens is the gas that's trapped makes its way. Now it has a clear pathway to move its way out. But all of that fracking water, that's 6 million gallons, has to come out first. So that's called the, I think they withdraw, flowback. That's the flowback water is what they call it. And they collect that 6 million gallons of water as best they can. And we don't actually know what they do with it here. Typically, they will drill another well called an injection well, and they'll actually inject it deep into the subsurface, which is questionable, but that's just standard industry practice. Or they do evaporation ponds, and so then all those chemicals just go into the air. So once it's open and all of that moves out, then it's just open, and then all of that gas can move its way out. In the very first year that a well is open, it produces 70% of the lifetime of its production. So these are not necessarily like long-term, great producers. They need to be refracked, or you need to frack new wells. So to access those trillions and trillions of gallons of potential technically recoverable resources, I mean, the amount of wells that would need to be drilled are unimaginable. Okay. So then what happens at the surface is all of that material comes up, and then they're put into separator tanks, and it's basically just a density separator. So the water sinks, the gas floats, the gas is just stripped off and put into a compressor, and it's sent through the pipelines to the power plants where it's processed. So that's a very brief overview. Again, what we are mostly harvesting here is methane. And our wells are about 1 mile deep and up to 3 miles in the horizontal direction.
Actually, 2 miles in our formation.
Oh, okay. Thank you, Natasha. So Natasha's going to share a lot more about what's happening currently. Okay, May. So to close, these are some of the things that we need to be aware of that I would imagine, all this just feels obvious, but just to name them, water is huge. I mean, 6 million gallons to frack one well. We're already struggling with water. So I think we just need to be having really transparent conversations about these resources. The flowback water, obviously, and where it's being disposed, that's a concern. Wells can leak. They can leak underground. They can leak at the surface. They can be leaking methane into the air. They can be leaking chemicals into the aquifer systems. Obviously, it disrupts the habitats, degrades the ecosystem, can create its own seismicity. And again, in our area, that really does have a potential for triggering landslides. So it is a sincere hazard. It's not just, we're trying to grasp at straws to find a way to move forward. This is actually serious and really kind of been brushed under the rug in the interest of, let's get all the gas out that we can. The regulations are quite loose. Again, Natasha is going to talk more about what's happening currently. And just lastly, things fail. And once a well has been capped and abandoned, they're not typically monitored, or they don't go back and look and see how are things doing, is it leaking, all of that. So it's a lot to consider. Okay. Okay. So very lastly, so the intention of the talk today is to educate you and to inform you and to inspire advocacy. And we do need to be taking action. And so I have some invitations for you. And of course, this is in collaboration with Citizens for a Healthy Community. And they are doing so much to address these things. So we're going to take a field trip on July 31st. You can sign up. we're going to do that loop through the Piance Basin that we just looked at, provided the fire safety is okay that day. Yeah, because there's only one road in and out. So we're just going to go up to Overland Reservoir and then come around kind of down by the East Muddy Creek and then back through Somerset. So we'll get to see all of these places, and I can point out some of the features in the landscape that we've talked about today and see the actual well paths and what does that look like. If you haven't been back there, it's beautiful. It's a totally different ecosystem, feels like, than it is here. It's just more tucked in, you know, it's just really special. So then lastly, we haven't picked a date yet for this, but we will close with a community, we're calling it a community brainstorming event. And Natasha will talk more about this as well, but basically we are looking to identify areas of critical environmental concern. That's an ACEC, an area of critical environmental concern. And if we can identify as a community and map some of these places, given that we live on a map of our whole entire land is geohazard, I don't think it should be too hard to find some creative ways to identify and designate areas of critical environmental concern in our area. So that is the goal. Yeah.
I want to go back, but so I don't know if it's a good time for a question.
Okay, give me just one second, because I think that's it. I just want to close with a quote, actually. May, if you can just take the last slide. This is one of my favorite quotes. So, thank you for being here, and just the reminder that we are here by geological consent, subject to change at any notice. So may we approach our landscapes with humility and respect and gratitude. Thank you.
What does the quote say? I can't read it.
It says, civilization exists by geological consent, subject to change without notice.